We've finally started to encounter some new types of simple systems that we haven't seen before. Now, in this video, I'm going to tell you that there are also some new control operations that we haven't seen before. And you might find that startling since earlier in the course I emphasized that there are exactly two control operations in classical thermodynamics: adiabatic work operations and various kinds of joins. So what's happening? Why are there new kinds of control operations here? The answer involves a concept that we introduced in the last lecture: reservoirs. So I want to start basically by giving you an example that hopefully will help you understand why maybe we should think about some other types of control operations. Let's go first over here and look at a couple of equations that will help us out. Recall that for the ideal gas, we have S, and I'll say the monatomic ideal gas, we have S is equal to N Kb times the log of sigma V over N U over N to the 3 halves plus 5 halves NKB. Now imagine that we want to do an adiabatic work operation on this system while fixing N. In other words, we want to change U and V at the same time in such a way that we don't change the entropy. What we can see here is that this V times U to the 3 halves power in the argument of the logarithm must stay the same. So that implies that U to the 3 halves times V is a constant. Now, if we wrote that constant as, say, alpha, we could say that for our adiabatic work operation, we have U is equal to, well, I would set this equal to alpha, then multiply by V inverse on both sides. So I'd have alpha V inverse on this side. Then I would multiply by the, I would raise each side to the 2/3 power. Since alpha is a constant, alpha to the 2/3 is just some other constant. So let's say that at the end of the day, once I've redefined that new constant to be alpha, I just get U is equal to alpha V to the minus 2/3. All right, wonderful. Now, furthermore, suppose that we have actually, let's back up. Furthermore, remember that for the ideal gas system, U is equal to 3 halves NKBT. In other words, for a given temperature, the energy is always the same. It doesn't depend on the volume it doesn't depend on the volume anyway. So, okay, good. Let's suppose that we start our system off with an internal energy U0, which I've depicted here. And furthermore, let's suppose that we have a reservoir with exactly the temperature that the simple system starts out with. So we can use that reservoir to bring that system back to energy U0 whenever we want. What I'm going to do, and let me grab a new color. What I'm going to do is the following. Let's suppose that we start at this point. So this will be our V0. Now this U is equal to alpha V to the minus 2/3 will just look like a downward facing curve of some kind, like this. So let's suppose that I do a motion like that. That's an adiabatic work operation. Next, I'm going to rejoin my system with the reservoir. Notice that a thermal join of this kind will not change the volume, so we'll stay along this vertical line, which maybe I'll call V1. But we'll jump back up to U0. Now we can do this process again. And we can go on like that as far as we want. The net motion in the limit where our adiabatic work operations are very small is to move horizontally along this line. And notice in that limit, we have the temperature and energy now being a constant as we perform this operation. This justifies that what we could do is call this an isothermal work operation. And I want to point out why we might want to call it isothermal work. Now, we are still doing some work to the system. Every time we do one of these adiabatic work operations, we're increasing the system's volume and decreasing its internal energy. In fact, actually, we're letting, in this example, the system do work to us. But we could think about doing this process in reverse, in which case we'd be doing work on the system. But in any case, then the reservoir comes and it doesn't do work on the system because we don't have that notion, but it does change the system's internal energy, as we see by the fact that it jumps on this vertical line. So sort of both the user and the reservoir affect the system's internal energy. Good. So this is one way of thinking about a new type of control operation, this isothermal work operation. I want to mention another one that maybe gets a little bit more at why this is a thing we might want to think about. And that is, to simply think about the scope of possible adiabatic work operations. Let me write the total entropy of the system that we were just working with, which is composed of one monatomic ideal gas and one reservoir. So we'll have S is equal to NKB log sigma V over N U over N to the 3 halves plus 5 halves NKB. But remember, we also have a thermal reservoir now. So we'll say plus, let me say that the constant of proportionality is now A, U, and then we could say plus some B, but I'm actually just going to leave it. It turns out it won't affect anything here. So we also know that A, what I've called A here, is in fact the 1 over the temperature. So let's actually just put that in right away. So plus U over T. Just to be clear also, let's say that this is T of the reservoir, T sub R. Okay, wonderful. So this is the total entropy of the whole compound system, composed of the sum of the two entropies of the internal, or of the two systems. I also realize that I should make this UR, and we'll just leave U as the internal energy of the main system. Now, if I wanted to do an adiabatic work operation on this main system, like I did here on this side, well, I would get exactly what I saw here, where we have U to the 3 halves times V is constant. The reason being that we need to keep the argument of this log constant if that entropy is going to be constant. But in this case, we now don't need to do that, right? Because we only need to, for an adiabatic work operation, to keep the total entropy of the system constant. That's our only requirement, I guess, beside the fact that we have to be able to do things continuously. So in this case, notice that if we do something in contact with the reservoir, with the thermal reservoir, and by do something I mean do an adiabatic work operation, then U here must stay fixed because U depends only on the temperature. So what I can do, since I know temperature will stay constant as long as we're in contact with the reservoir, is rewrite U as 3 halves NKBT. Okay, so now notice that the argument of the log can't stay constant if I start to change V. The only thing that I can do to compensate is start to change the internal energy of the reservoir, which won't have any effect on its temperature. So unlike the ideal gas system, for the reservoir, the internal energy and the temperature are not coupled. So now let's say that I want to increase the volume to V prime. So S afterward, let me just say S prime is equal to NKB log sigma V over N. After I do this replacement, I'll get 3 halves KB T, which stays the same. And I should have had V prime here, sorry. And notice the ends have canceled here. So then just to the 3/2 plus 5/2 NKB plus UR prime over TR. Now, I had mentioned before that I wanted to be clear that TR was the temperature of the reservoir, but now that we're saying that everything is happening with the reservoir and the main system in contact, it should be clear that TR is equal to T. So let's erase that subscript now that we've made the point. Good. And we see the following. If we want to increase V to V prime, we can always compensate by somehow changing UR prime. Since that's within our purview as the user, we can always change things in such a way that we're only doing coarsework on the system, only changing internal energy coordinates and work coordinates. We're fine. This is a possible adiabatic work operation. So we can see that there are two ways to view an isothermal work operation. We can either see it as us doing continuous adiabatic work operations followed by thermal joins on the system, or we can see it as one adiabatic work operation that we're doing on the compound system. The reason that this is a sort of interesting way to think about things is that if at the end of the day we forget about the state of the reservoir, it means that we can simply think about changing V internally here without worrying about anything else, as long as we also keep T constant in the main system's entropy. Okay, so just to be careful, to be clear, for an adiabatic work operation, we know that delta S is 0. We're learning that for an isothermal work operation, delta T is 0. And now it's a good point to note that we also have the notion of an isobaric work operation. So an isobaric work operation is a work operation done at constant pressure. Moreover, we could have any kind of equal PI work operation if we were in contact with a VI reservoir. And so we have this whole scope of new kinds of thermodynamics that we can do. I want to actually also draw this up in a little table, which I hope will clarify some things that we get into a little bit later in the semester. So here we go. Now, what I'm going to talk about here, two of these columns will be control operations. So here we'll put the work operation, and here we'll put the join operation. Okay, so so now in this column, we'll put what reservoir type we're in contact with. The first thing that we encountered was the case in which we are not in contact with the reservoir at all. In that case, we could do an adiabatic work operation and an ordinary join. Let me just say ordinary here, although I won't define this carefully. It's just exactly what we've seen. What we know about the ordinary join operation is that it maximizes entropy on our subspace. So let me put that here as maybe a little note. Max entropy. Now we've introduced a couple of new possibilities. We have an isothermal work operation. And so I should say thermal reservoir. which allows isothermal work. And we'll leave this box empty for now. We'll have to fill that in a little bit later once we've gotten some more physics under our belts. All right. We can also have a mechanical reservoir, or a V reservoir, in which we have an isobaric work operation done at constant pressure. And same thing here. We're just going to have to wait to fill in this part of the table. Finally, we see that we can also have just any VI reservoir induce a type of work operation done at that constant PI. So this we would call equal PI. I'm opting to use the English word or Latinate word equal here rather than the Greek prefix iso, just because I think it makes it a little bit clearer. But it's exactly the same thing going on here, right? Isothermal equal temperature, isobaric equal pressure. Good. And likewise, we're going to have to cross that out for now. In any case, I hope that this starts to get you thinking. We can kind of come up with a different sort of set of control operation rules for contact with each type of reservoir. And that's very important because oftentimes we'll have a reservoir that's naturally coupled to the system that we're working with. One example is to think about doing a sort of laboratory experiment in a lab. Typically, our lab equipment will be at some temperature. Often it will be room temperature, but it might be some other temperature as well. Like if we're doing a low temperature experiment, perhaps we've coupled our experiment intentionally with something that is of lower temperature than the room, like liquid nitrogen or liquid helium. Additionally, an isobaric operation might be very common as well. If we're doing a tabletop or a bench experiment in chemistry or something like that, then maybe our beaker is open to the atmosphere, such that without us having to do anything, we're doing all of our control operations at exactly atmospheric pressure, if we're at sea level. So in any case, there's a real reason to be thinking about reservoir contact and the different control operations that we get in those cases. I'm very excited to go and try and fill in these boxes later in the course. But for now, I'll say thank you so much for watching, and I'll see you in the next one.